Hello, my name is Aaron Comas. I am here doing an extra credit assignment for IE546, Economic Decisions in Engineering at Purdue University. The assignment that I am working on is the multi-attribute utility theory of the purchase of a family car. I'd like to start by talking about the decision context. So I have a growing family and I'm in the market for a new family vehicle. After all, the dogs need to go somewhere for our road trips. Due to the sunk cost involved with purchasing a new car to begin with, I am looking for the best long-term investment. So this means that a minor increase in upfront cost is worthwhile for the long-term cost savings. Therefore, the time horizon will be over the next 5 years. In order to ensure that I was able to identify the correct attributes, I started by developing a fundamental and means objectives hierarchy with the goal of picking the best new car available. The fundamental objectives involved maximizing safety, maximizing reliability, and minimizing overall cost. These were achieved via the means objectives involving maximizing visibility, maximizing safety features, maximizing engine life, and performing regular maintenance. When we transfer those fundamental objectives into the primary attributes that we will be assessing, we end up with 3 attributes of interest: the cost to own, safety, and reliability. For cost to own, we're talking about units of US dollars. The source will be Edmunds. Edmunds will account for all sorts of costs associated with the 5-year time horizon of a cost to own, including insurance, maintenance, upfront cost, interest, etc. For safety, we will be going off of the unit list score provided by US News and World Report. And finally, for reliability, we will be looking at the score provided by J.D. Power's reliability. We have 3 primary alternatives that we will be considering. This involves the 2023 Subaru Crosstrek, the 2023 Hyundai Santa Fe, and the 2022 Jeep Wrangler Unlimited. In terms of setting up our utility function, there are several assumptions that we want to identify up front. We will be assuming simple additive utility functions, and we are not necessarily assuming linear. It will come down to the best fit based upon the utility values that we define. We will be assuming additive independence, and the trade-off comparisons will be assessed via direct assessment. This is typically a good approach for simple problems, and we'll be using a set of comparison lotteries for each possible combination in order to determine what the intermediary utility value should be. We'll start with the cost to own utility setup. In the table on the left, you can see the 3 alternatives: the Crosstrek, the Santa Fe, and the Wrangler, along with the associated 5-year cost to own. The known equivalence values will be a utility of 1 for the most desirable cost, which would be the least cost, around $40,000 for the Crosstrek, and the utility of 0 will go towards the most expensive and least desirable attribute, which will be for the Wrangler at just over $53,000. Through the use of lotteries, we were able to identify a personal utility of approximately 0.3 for the Santa Fe at around $50,000. Similarly, we follow the same format with the table on the left showing what the safety score is for our 3 alternatives. The same approach will be taken with the most desirable attribute, such as the 9.8 value for the Santa Fe having a utility of 1, and the lowest score for the Wrangler being a 7.3, getting a utility of 0. Again, we use lotteries in order to determine what the personal utility is, which is approximately 0.7 for the Crosstrek. Finally, we'll look at the reliability for the three alternatives, where the highest utility of 1 will be scored for the Wrangler with the highest reliability score, and the Santa Fe will receive the lowest utility score of 0 since it has the lowest associated reliability score. Our lottery will determine a personal utility of approximately 0.5 for the Crosstrek as the intermediary value. We'll start with utility realization for our first attribute of cost to own. We'll start by eliciting all single attribute utility functions. By plotting the three utility values that we identified earlier in this presentation, we're able to fit a curve to those data points. We have a perfect fit with an r-squared value of 1 for a quadratic, and that quadratic equation is shown here. We take the first and second derivative of that equation, and we end up dividing out the second derivative from the first derivative in order to determine what our risk equation is. By assessing whether the risk equation increases or decreases with x, we're able to confirm via equation and via plotting that the cost to own is consistent with risk-seeking behavior. We complete similar work with the safety attribute, where we fit all three data points for safety that we identified earlier to a graph. And with an r-squared value, we're able to confirm a quadratic fit. We take the first and second derivative again, we calculate out the risk, and we're able to show both numerically and graphically that for safety, the decision maker is risk averse. Our final utility realization is for the reliability attribute. We fit all three data points, and we are able to confirm with an r-squared value of 1 that, in fact, our equation is best represented by a linear plot. We take the first and second derivative, but because this is a linear utility function, our second derivative is 0. Therefore, our risk is 0, which confirms both numerically and graphically that the decision maker is risk neutral when it comes to the reliability attribute. Now that we've determined our utility functions for each of our attributes, we're going to fit the multi-attribute utility function using these single attribute functions. So you can see that we have our utility function represented by x, y, and z. You may have noticed in the earlier charts that our cost to own is the x variable, our safety attribute is our y variable, and our reliability is our z variable. Therefore, we're able to show that when you add up kx, ky, and kz, we're consistent with equaling 1, which is one of our boundaries that we must meet. We're then able to set these equations consistent with one another at a point of indifference to be able to get our two other equations such that we have a 3x3 matrix that we can do some basic algebra for to determine what our kx, ky, and kz values are. You can see those in the bottom with kx equaling 0.374, ky equaling 0.257, and kz equaling 0.369. This is consistent with our initial boundary condition of all three k values equaling 1. The final step is to take our multi-attribute utility function and apply the various utility values that were determined earlier in this presentation into our composite utility function with the associated weights that we calculated on the previous chart. The results here are shown in the table on the bottom, and we can see that the highest expected utility is for the Crosstrek, meaning that the Subaru Crosstrek is the rational choice for purchasing of a new family vehicle.